Controlling microgrids is essential because it allows to keep the system stable. Control makes possible to optimize power generation and consumption considering external factors, such as market prices. In this video, we will talk about hierarchical control, and we will see what are some different control strategies that can be used in microgrids. You will learn what is the role of primary, secondary, and tertiary control in microgrids, and how these three levels are combined in a hierarchical way. Then, we will see different control strategies that are generally implemented in microgrids. Among them, we're going to distinguish between grid forming and grid feeding strategies, and we're going to have a look at the concept of master-slave control strategy. As seen in previous videos, a hierarchical control scheme typically comprises primary, secondary, and tertiary control. Primary control loops are mainly concerned with the inner loop, outer loops, and the implementation of drip control. Secondary controllers are employed to adjust the reference points of their distributed generators in a microgrid. Also, they are used to synchronize a microgrid with the external grid. Tertiary control mainly addresses the exchange of power between the microgrid and the external grid, taking into account electricity market and regulatory signals. Here we can see a better example of the implementation of primary, secondary, and tertiary controls in a distributed generation system. Local control acts on power electronics interfaces that connect generators, loads, or batteries to the microgrid bus. The control that acts on the power converter here, DC to AC inverter, is based on voltage or current. On the very high level, tertiary control provides the unit with active and reactive power set points considering market and price signals retrieved from the transmission system operator or the distribution system operator directly. At this level, control is responsible for the optimal power flow in the microgrid. For example, it is possible to determine if it is more economically beneficial to sell power to the main grid or to store it. On an intermediate level, secondary control adjusts the active and reactive power set points. This fast and accurate control has the aim of detecting and counteracting grid instabilities. At the lowest level, local control or primary control is implemented internally in a distributed generator in a decentralized fashion. Primary control is the main responsible for controlling active power and reactive power in microgrids. The value of three-phase currents and voltages are retrieved from the grid and sent to the controller. Finally, a distributed generation unit might provide extra ancillary services to the microgrid. Inertia emulation is one of the typical ancillary services, as well as power oscillation damping, support of islanding operation, and power quality issues. Various control strategies are adopted to create a microgrid. It is possible to identify two types of distributed generation control: grid forming and grid feeding. Grid forming types fall into two groups: communication-based and non-communication-based control schemes. Among communication-based control strategies, master-slave control is widely known as, and it is an alternative to drip control. Drip control is a non-communication-based control strategy. In the next video, we will see drip control strategies in more detail. Grid feeding types are typically implemented using synchronous reference frame, stationary reference frame, and natural frame. We have seen already that through a Clark-Park transform, it is possible to adapt a three-phase ABC signal into a stationary frame alpha beta, and then into a rotating DQ frame. The DQ rotating or synchronous reference frame is used when proportional integral controllers, also known as PI, are implemented. Stationary reference frame alpha beta is used to implement proportional resonant or PR controllers. Finally, natural reference frame ABC for three-phase systems can be used for a wide range of controllers like hysteresis and deadbeat controller. The master-slave control strategy is a mature solution for the parallel operation of several distributed generators in microgrids. The master unit is represented by a grid-forming type, which dominantly controls the voltage and frequency of a microgrid. Grid-feeding units, called slaves, mainly follow the voltage and frequency imposed by the master unit, while trying to follow their active and reactive power set points. Moreover, both types of grid-supporting units can be connected to such microgrid in a flexible way. In any case, a supervisory control is needed to appropriately divide the power among all units. The main advantages of the master-slave control strategy are its simplicity, being quite straightforward to implement, and its robustness. However, the system cannot be easily expanded, and the supervisory control is needed to always share the power in a proper way. Importantly, this control strategy relies on communication technologies, which gives lower reliability due to the uncertain communication links. To overcome all these problems, a multi-master control strategy is often proposed. So, in this lesson, we'll learn that local control in microgrids can be hierarchical. It is usually divided into primary, secondary, and tertiary control. Then we saw how these three layers are implemented, what are the areas involved, and the microgrid parameters over which the different controls act. Next, we had a quick overview of the different types of grid-forming and grid-feeding control strategies. Finally, we learned that the master-slave control strategy is one of the most mature technologies for the parallel operation of distributed generation in microgrids, making use of grid-forming and grid-feeding units. In the next video, we will go more in depth into this control strategy.